All right, let's take a look at inductors, capacitors, and resistors in our AC circuits. We're going to call these an RLC circuit. We're going to put our three components, the resistor, inductor, and capacitor, in series with an AC source. What's going to happen in this case? All right, well, we learned in the previous sections that for the inductors and capacitors, the voltage and current were not in phase. So that means that if you have all three devices here, the voltage R, L, and C here are not in phase. They don't reach their maximum at the same time. It turns out that if you want to find the total voltage across the combination, that you cannot simply add them even though the devices are in series. To add them, you have to use this formula, which kind of looks like the Pythagorean theorem. It's a result of phasor addition, but we're not going to derive this. We're just going to accept it that the voltages add up differently because they're not in phase. So then what we do is, from each of these voltage terms, we can factor out a current, take it out of the square root. And now I have a note, does this look like Ohm's law? Well, it doesn't really, but it kind of does, because you have voltage equals I times all of this. So usually we have a voltage equals a current times a resistance, if you just have a resistor in a circuit. So if this somehow is similar to resistance, then we can see Ohm's law here. So what we do to make this look like resistance, we give this a name, and we're going to call it impedance. This square root measures the opposition that the elements present to the current when the voltage is applied. Any opposition to current is like a resistance. So you can think of impedance as the AC analog to resistance in a DC circuit. So when you have those three components in an AC circuit, they have an overall resistance effect on the circuit, and we call that the impedance. And it has units of ohms, just like the resistance, inductive reactance, and capacitive reactance. When using this equation, and we're going to do an example very soon, but just make sure that the square is outside of the difference of the two reactances. Do not square the individual reactances. Some people like to do that, so don't do that. So we can use Ohm's law for the RLC circuit, V equals IZ. So if we know the voltage and the impedance of the whole circuit, then we can find the current through the circuit. So just think of the impedance as a resistance for the whole circuit. Let's go ahead and do an example. We have a 60 volt, 100 hertz line, AC line, connected across a series RLC circuit. We're given R, L, and C. So 100 hertz, that's the frequency. And then we learned that if we're given the voltage of our AC line, that voltage is actually the RMS voltage. Remember the 120 volt line that we get from our outlets? That 120 volts, that's the RMS voltage. So the first thing that I ask for is the inductive reactance. So this is a plug and chug inductive reactance. XL equals 2 pi F times L. So plug in 2 pi times 100 hertz times 10 henries, and that's going to give us 6280 ohms. That's the inductive reactance. And then the capacitive reactance, X sub C, is 1 over 2 pi FC. So once again, plug and chug, 1 divided by 2 pi times 100 times the capacitance, which is 2, times 10 to the negative 6. So 1 over all of this is going to give us 796 ohms. The second part says, what's the impedance of the circuit? So we just learned about impedance. Z equals the square root R squared plus XL minus XC squared. So plug and chug, the square root of 1000 squared plus 6280 minus 796, all of that squared. Then take the square root after you add these two terms, and we're going to get 5570 ohms. That's the impedance for the circuit. Let's keep going. There's a couple more parts here. Find the RMS current in the circuit. Well, the current using Ohm's law is going to equal V over Z. Since we have the RMS value of the voltage, that will give us the RMS value for the current. So all we have to do is 60 divided by 5570 ohms that we just found. That's going to give us 10.7 milliamps, or 10 to negative 3 amps. And finally, the RMS voltage drops across R, L, and C. So what's the voltage across the R, the resistor? It's going to be I times R. So multiply this current that we just found, 10.7 times 10 to negative 3 times 1000. That's going to give us 10.7 volts. And then the voltage across the inductor. That's going to be the current times the inductive reactance. So same current here, 10.7 times 10 to negative 3. Then the inductive reactance that we found was 6280 ohms. Multiply those together, that's going to give us 67.6 volts. And finally, the voltage across the capacitor is the current times the capacitive reactance. Multiply that current that we just found times the capacitive reactance that we found earlier, which was 796 ohms. That's going to give us 8.52 volts. So you can see that the voltages definitely don't add up to the 60 volts, but that's because they're not in phase. They don't reach their maximum at the same time. That's all for this section. The last section we'll be looking at resonance in our AC circuits.